All right, so I wanted to show you first tinyclr.com/forum. If you have questions, this is a great first place to start. The other thing is that once you install the starter kit software on your machine, one of the things that you will have is you go to Start All Programs. In this case, since it's a GHI starter kit, GHI Electronics, GHI .NET Gadgeteer SDK, Bez Spider starter kit, getting started. That will take you to this page, which is local. Until I got to here, I was completely lost when I got the starter kit. I got the starter kit, and you open up the box, and there's a card that points you to tinyclr.com, and there's no other documentation. And so you look at it, and you kind of go, okay. Well, there's a wiki at the GHI site, which is very useful, got a lot of good information. And finally, once I realized, okay, here are all the things I have to install, now what? And then I realized, okay, now I got to go to this. Once I go to here, this actually walks you through building your first .NET Gadgeteer device, which is your basic digital camera. So it's a very nice, detailed, step-by-step walkthrough of connecting all the parts, all the different pieces, all the good stuff, including the software.
So you already said your basic digital camera. I mean,
So literally, when I bought this kit, I got it in my house. I had to open it up same day. I actually did a neat unboxing video on my blog, devhammer.net. You can take a look at. From the time that I had the SDK and software installed to the time that I had a working digital camera from these components was literally about 10 minutes. The beauty of this platform is the ability to do rapid prototyping and just get creative with ideas, get nuts with things that you never would have thought to do with just a PC, because you've got all these components that even if you've got all of these various things that are pre-plugged in, all these modules, even if none of those does exactly what you want to do, that's fine. Do like Pete did, break it out to a breadboard, and then you can go to town. You can build your own circuits, breadboard them, and then build a diagram and have somebody fab up a circuit for you. Pete's actually, this is his geek cred, Pete has actually designed and had built for him a printed circuit board for a MIDI breakout box that he designed. So he's a little more hardcore on the hardware stuff than I am. I'm just excited because I'm a guy who comes from the VB background. I'm somebody who I don't have a CS background. I don't have an EE background.
it shows.
I'm a developer. I'm a hacker-style developer. Yeah, this is actually Danny, who's one of my coworkers. He's a fellow DE who should be nicer to me. So I don't have a formal, computer science background. I got into this. I learned a lot of this stuff, sort of as I go along, and it's extraordinarily exciting to me that there's this thing that allows me to plug these pieces together with relatively little chance of releasing the blue smoke, and a real high chance of building something awesome, and being able to actually run that in power. So we're going to skip the starter point here, and I'm going to start with a demo that sort of takes a step beyond just the pure Gadgeteer. So you jump back here, real quick back to the GHI site. If I flip over to their home page and look at the .NET Gadgeteer category, you can see they've got the .NET MicroFramework Fez stuff. If I go and look at the main board and kit, you can see there's the Spider starter kit, which is about $250, the Spider main board. The Hydra basic kit is coming out soon. It's not quite available yet, but as you can see, the Hydra main board is a little bit cheaper. In terms of modules, you have a very large selection of modules already, and this is a brand new platform, so to see this much hardware variety is really cool. So you have buttons, LEDs, Ethernet, Wi-Fi, SD, joystick, extender, potentiometer.
Joystick like a mouse pad joystick kind of? What kind of?
So you could actually, with a USB host, with the appropriate driver, you could do mouse, keyboard, any of the above.
This is a joystick right here.
Yeah. Yeah, and so you could use that for directional control.
Something with
Yeah,
that.
you could use that for directional control. There's all kinds of sensors in here. There's the compass. There's the current module, GPS.
Motors?
What's that?
Motors?
Motor controllers.
Yeah.
So there's actually a motor driver that's coming out at the end of November. There's a relay module, so you can just basically turn on, turn off power. The motor driver is going to give you more of the pulse width modulation, speed control kind of thing. There's a music module, so you can play back MP3 and waves and OGG and all that good stuff. But what happens when none of these modules does exactly what you need? Well, one of the kits that they also offer is this E-block kit. And the E-block kit is fantastic because the E-blocks are sort of an older format of components that GHI offers. They're a 3-wire, basically one pin, one-to-one pin to the various parts of the processor. But they include things like LEDs. Yeah, you got some LEDs in the kit. POTS, piezos, light sensor, IR sensor, IR LED, temperature sensor. Am I missing any?
It's just pretty much everything.
Yeah. And so what GHI has done is they've created this E-block extension or E-block expander module that allows you to plug in E-blocks and then plug those into the Gadgeteer board. And so you can expand on what is offered just purely by the .NET Gadgeteer stuff with some external components as well. So what I want to show you here, this is a project that I put together to demonstrate some of the features here. And basically the first demo I'm going to do is just using these two piezo buzzers here. And I'm going to walk through, let me demonstrate it first and then I'll walk you through the code. So this is going to reboot my, my processor here and then deploy the code. And you'll also know, because you've got that debug statement that says program started, this is how I tell when I'm debugging that I'm actually running. It's a nice way of saying, oh yeah, okay, now I'm running. So now I can test this.
Let me just stop that one.
Sure.
So I don't know if you caught what's actually happening there. The board has a debug print statement or a debug.writeline statement running on it that is then reflected in the output window of Visual Studio.
Right.
You're not simulating this or anything like this. You are actually debugging the board from your PC. It's running on the board and it's, there's some messages going back.
So anybody who's done programming, for example, for Windows Phone, same sort of idea. You're actually running the code on the device, but debugging live through the IDE.
You
So
can
we're,
step through.
right, and in this case we're communicating over USB, but you can do it over network, over serial. Yeah.
Just out of interest, and I just noticed that, one of, set of the assemblies that it's debugging is Microsoft.Spot. Is this running on the same spot as the watches?
So yeah, so that's a good catch. So you'll see they never bothered to change the namespace. Some of this code originated as the Spot, the smart personal object technology that was originally created for the smart watches that ran on a sideband of the FM frequency, and you could download news and email and things like that onto your watch. I actually still have 2 of them. I don't wear them anymore, but I do still have 2 of them.
I didn't even know about it.
What's that?
When was those?
This is probably, I think they were discontinued probably within the last couple of years, but probably about 5 or 6 years ago they were.
2002.
What's that?
2002.
2002? They were discontinued then?
No, that's when they were supposed to hit.
Yeah, so it's been a while. But that was where this idea of the tiny CLR got its start. And actually, if you went into the menus in your Spot watch, you could actually see that that some of the code that was running was tinyclr.dll or something of that nature. So this technology got its start with that idea and has simply grown from there. All right, so I'm running my code on my processor. I've got it set up so that I need to click a button. So I don't have my stuff neatly pinned down the way Pete's is, but so I've got my button. I'm going to press it. So I'm playing a tune on my piezos.
Can you guys hear that?
Yeah.
Okay, so on the piezos, I'm playing a simple scale up and down, and what I'm doing to do that is when my button press event takes place, first of all, I've set up my piezos by saying, piezo 1 is this E-block expansion. Then I say set up PWM output. PWM is pulse width modulation. In order to interact with things like motor controllers, if I want to control speed or the piezo button, I need to do pulse width modulation output to that device. So when I call set up PWM output and then pass in the number of the pin that this is connected to. So in this case, my E-block expansion with no suffix is this guy right here, which is connected to socket 9. So if I trace that, yes, so it, no, that's wrong, sorry. That's an E-block expansion 2, sorry. E-block expansion is plugged into socket 11, which is right here, which will trace to this guy right here. And then each of these sockets on the E-block expansion maps to a pin in this 10-pin plug. In this case, a couple of the pins are used for power, so you've only got access to 3 through 9. 3, 4, and 5 are analog, the rest are digital. So in this case, I'm plugging into the digital pin 8. And then inside the software, I tell it which pin I'm connecting to. So that's all that the software needs to know to communicate with this piezo. So I give it the piezo name, and then down in my button handler, I'm calling piezo set, and I'm setting the frequency that I want it to buzz at. And this is the duty cycle. I'm just setting that to 50.
Is that in milliseconds or?
No, this is a frequency in terms of like sound. So
The second
for example, concert A is 440.
It's hertz.
Right? It's 440 hertz. So I'm starting from, I forget, I've used a chart for this. I think I started at C and then went up from there. So I'm basically going up to A, and then, up to, there we go, up to 523. So I'm doing basically a scale up and then a scale down, and I'm alternating between the piezos. And I'm turning off by setting the duty cycle to 0, whichever piezo is not currently sounding. So the idea was to get sort of a ping pong sound, which is a little hard to translate out to the audience, but you get the point. Now, another thing that I can do is I can take inputs and use them to impact outputs. So I'm going to go ahead and comment this section out.
You guys, you know those like dancing Santas and stuff like that? So you could totally make one of those with these, because what Andrew was doing for how it makes music out of that is the same way a lot of those do. They either use a recording or they use pulse width modulation to just beep out a tone.
Right. And if you've ever gotten those greeting cards that have sound in them,
Yeah.
the early ones, I mean, now they've got some that are actually using digital signal processing, but the earliest ones,
It's still running.
yeah, no wonder it's not letting me comment.
Yeah.
Ah, thank you. Wow.
Edit and continue only actually works on the hardware side of things.
Actually, edit and continue would work if this was VB. Just saying. All right. So what I'm going to do now is I'm going to switch to a timer-based model, and I'm going to add in some potentiometer inputs. So I'm setting up a timer to tick every 100 milliseconds. I've got a couple of potentiometers, which you can see here. These are also E-blocks. These are plugging in to analog ports on a separate expansion module. Now, the trick with some of the E-block expansion modules is it's tough sometimes to mix and match analog and digital inputs, because each of the sockets has particular features that it exposes. So if you need to use features that are only on different ports. So for example, my piezos are plugged into ports that have a P for pulse width modulation. So both 11 and I think that's 8 both have the P on them. Those are the only ones that will drive the piezos. Meanwhile, the pots need to have an analog pin or A, so that's plugged into port number 9. So then I'm basically saying my pots are plugged in pins 3 and 4 on E-block expansion 2, which is plugged into socket 9. And then I'm going to basically turn the proportion of the turn on the pot into a percentage, which I'm going to use to alter the frequency on the piezos. And I'm going to do that each time the timer ticks. So I'm basically polling the potentiometers and resetting the pitch that the piezos are doing, and I'm going to do that each time the button is pressed. I'm going to turn the timer on or off. So let's run this.